Let's tackle 4-2 logarithmic functions. Okay. Every one-to-one function has an inverse that is also a function. We talked about inverses back when we were doing polynomial functions. A one-to-one function is one in which each x is assigned to a unique y value. Each x value is assigned to a unique y value. One-to-one functions are going to pass both the horizontal and vertical line tests. So, for example, if you remember when we were graphing polynomial functions, when we had our quadratic functions, our parabolas, they passed our vertical line test. Each x has only one y, so they pass the vertical line test, but they fail the horizontal line test because each x is not assigned to a unique y value. So our parabolas are not one-to-one. Exponential functions, however, are one-to-one functions. Their inverses are also functions. They are logarithmic functions. How do you find the inverse of a function? Well, we had a couple of different methods. We could use the switch and solve, where we switch out the x and the y, and then we solve for y again. Or you could think about reflecting it over the line y equals x, that positive diagonal line. Or you could exchange literally the domain and range, so the x and y columns. Or if you have a set of points, you could switch out the x and y and graph the corresponding inverted points. Okay. Graph the parent exponential function, base 2, and its inverse log function. So my parent exponential function, base 2, inverse log function is also base 2, but that base shows up in a different place. Now the base is down at the base of the log statement. So f of x equals 2 to the x. We've already graphed this before. Let's go ahead and fill it in and graph it again. Remember, when I'm graphing exponential functions, I use those standard, I want to switch colors. I use those standard 5 values for x. So I'm going to use -2, -1, 0, 1, and 2. When I do 2 to the -2, I get 1/4. 2 to the -1 is 1/2. Anything to the 0 is 1. 2 to the first is 2. 2 squared is 4. So those are my 5 points that I will graph that give me my exponential increase for that exponential function. All exponential functions have a domain of all real numbers. And my parent exponential functions have a range from 0, not included, to positive infinity. So that's my starting place for the parent exponential function. I've got -2 to the 1/4, -1 to the 1/2, 0, 1, there's my y-intercept that we focus on. 1 squared, 1 is where x is 1, y is 2, where x is 2, y is 4, and I've got my exponential increase. So my exponential function base 2 looks like this. Okay, let's think about our inverse of that. Our inverse of that is going to be a log function, where my exponential function is f of x equals 2 to the x. My log function is going to be g of x equals log base 2 of x. I'm going to exchange the domain and range. So I take my lists and I switch them. X was -2 to +2, now that's y. Y was 1/4, 1/2, 1, 2, 4, now that is x. And I graph those 5 points. Remember that when I reflect my inverse, it reflects across the line y equals x, that diagonal line right there. So I do expect to see that reflection happen as I plot these 5 points. All right, be careful as you plot that you're paying attention to what is x and what is y. I'm going to start with the easier points. I'm going to start at the bottom. Where x is 4, y is 2. Where x is 4, 1, 2, 3, 4, y is 2, right there. That's the reflection of that point. Where x is 2, y is 1. 1, 2, up 1. That's the reflection of this point. where x is 1, y is 0, right here. That's the reflection. What was the y-intercept is now the x-intercept. Where x is 1/2, I'm at -1. 1/4 is at -2. And I found that I'm approaching no longer a horizontal asymptote. I'm approaching a vertical asymptote. That this function reflects across that line y equals x. And I have corresponding points. This point on my exponential function was 0, 1. The corresponding point on my log function is 1, 0. This point on my exponential function, we'll just do this one, is 2, 4. The corresponding point on my log function is 4, 2. It still has an increase. It's an increasing function. Let's do some of this. It's an increasing function. Increasing function. What was the domain of the original function is the range of the inverse. And what was the range of the original function becomes the domain of the inverse. For my exponential function, I had a horizontal asymptote at y equals 0. For my logarithmic function, I have a vertical asymptote at x equals 0. Right there is my vertical asymptote at x equals 0. One thing that you need to remember when you're working with logarithms is that the answer to the logarithm is always the exponent of the base. The answer to the logarithm is always the exponent of the base. Let's look at the next page to see what that means. Okay, we've got some blanks to fill in here. Definition. Just like we had a definition for our logarithm, a definition for our exponential function, we have a definition for our logarithmic function. Our logarithmic function, base a, is read, f of x equals log base a of x. X and a are still real numbers, just like with an exponential function. X is greater than 0. A, just like with my exponential function, a has to be greater than 0 and not 1. So my base still has to be a positive value, not 1. There are 3 pieces of information that switch places when we're converting back and forth from an exponential function to its inverse logarithmic function. Three pieces of information. That's all I have to keep track of. 3 pieces of information. We have a base in exponential form. You have a base raised to an exponent, and the answer is the logarithm, is the argument, I get distracted. Have a base raised to an exponent, the answer is an argument. This is my exponential form of the equation. So, for example, if I want to do something that I'm familiar with, put it in numeric form, let's use base 2, exponent 3, and what is 2 cubed equal to? Well, it's equal to 8. 8 is my argument. Now, those 3 pieces of information just rearrange. They change where they're located when I switch from exponential form to logarithmic form. Now my base is down here at the base of that log statement. Then I have the argument next, and that is equal to the exponent. Remember that statement on the last page where I said that the answer to the logarithm is always the exponent. You can see it right there. The answer to the logarithm is always the exponent. So I'm taking these same 3 pieces, 2, 3, and 8, and I'm just turning them around. It's like rearranging the furniture. So now I have this log statement, and it's going to be equal to something. Log statement, and then down here is my base. Right here is, I need to plug in my numbers. My base is 2. My base is 2. Right here, my base is 2. My argument, that's what comes next, is 8. And my exponent is the answer, 3. Log base 2 of 8 is 3. When I read that question, when I look at it, I'm asking myself, literally, when I see that log, I'm saying, what is the exponent of 2 that gives me 8? Well, the exponent of 2 that gives me 8 is 3. All right, let's practice thinking through that question a few times. Log base 3 of 9. When I read that, I'm asking myself, what is the exponent of 3 that gives me 9? That's the question I'm being asked. What is the exponent of 3 that gives me 9? Because the answer is that exponent. What is the exponent of 3 that gives me 9? It's 2. Some of these are not, we're going to have to do a little bit of thinking. We're still asking the same question. What is the exponent of 2 that gives me 1/4? Well, I'm looking for the exponent. Exponent of 2 that gives me 1/4. Well, how is 2 to some power related to 1/4? 2 squared is 4. Negative exponent tells me to flip it, so the exponent would be a -2. Remember, my exponent can be anything. Doesn't have restrictions on that. Number 3. Number 3 asks, what is the exponent of 1/2? Because that's my base. That gives me 8. Well, 2 cubed is 8, so I would need to flip this. Instead of 1/2, I would need 2. So again, I'm going to need a negative exponent. 1/2 to the -3 gives me 8. Some of you may be trying to plug this into your calculator and have discovered that there's not a button for that. That is absolutely the case. You need to understand how to solve these by thinking through the statement and by rearranging the terms. All right, the next one. What is the exponent of 4 that gives me 1/16? Well, 4 squared is 16, so 4 to the -2 gives me 1/16. What about this? What about the exponent of 2 that gives me -4? The exponent of 2 that gives me -4. Well, is there anything I can multiply 2 by that's going to give me a negative answer? No. There's no way to multiply a positive number, raise a positive number to some exponent and get a negative result. That can't happen. Remember, this -4 is my argument. It's always going to be positive. We said that back here in our definition, that argument x is always going to be positive. So, you know what? I need to change that because this is x. No, that's good. That x is always going to be positive. That's my domain that I'm putting in. We're right. That's not possible. That is just not possible. There's nothing that can make that happen. Okay, 3, what is the log base 3 of 0? Log base 3 of 0. When I rewrite that, I say, what is the exponent of 3 that gives me 0? Well, 3 to the 0 power is always 1, but there's nothing, no exponent of 3 that gives me 0. That is not possible either. And you can say not possible, or you can say undefined. Okay, let's talk about graphing logarithms. Graphing logarithms with transformations. Okay, so let's graph some log functions. We're going to do it by making a table and thinking about the given, the parent log function, but we're going to start with the inverse of the log function, which would be an exponential function, also base 2. Well, what would an exponential function base 2 look like? I am going to come over here and think about y equals 2 to the x. So that's an exponential function base 2. If I create my chart for my xy ordered pairs for an exponential function, I'm plugging in those basic 5 values for x, and I'm solving for y by applying these as my exponents. So 2 to the -2 is 1/4, 2 to the -1 is 1/2, anything to the 0 is 1, 2 to the first is 2, and 2 squared is 4. That's what it would be for an exponential function. To get the log function, I take the inverse. When I take the inverse, I switch the columns. So my x column, my domain for my exponential function, becomes my y column, or my range for my log function. The y column or range for my exponential function becomes the domain of my log function. Okay, and I'm going to graph these 5 points as my f of x, log base 2 of x. I've got x is 1/4, I'm at -2, x is 1/2, I'm at -1, and then I get to my x-intercept at 1, 0. Then I've got 2, 1, and 1, 2, 3, 4. I'm up here at 2, and I start my increase. I find my asymptote and my increase, and there is the basic shape of my parent logarithmic function base 2 with a vertical asymptote at x equals 0. The domain of this log function is limited by that vertical asymptote, so my domain is from 0 to infinity. The range of my log function is all real numbers. Remember, that's the inverse or the flip of what it would have been for the exponential function base 2. I have an x-intercept. My x-intercept is at 1, 0, and this function is increasing. Okay, now moving forward, it says for each equation, first sketch this parent log function, and then determine any transformations and use those transformations to graph that next function. So the very first thing I'm going to do is graph my parent log function f of x. So f of x has an x-intercept at 1, 0, and I'm not even going to put in the other points. I'm just going to graph the shape because I know what my log function shape looks like. That is my parent function f of x. Now we're going to attack the transformed function g of x. G of x is equal to negative log base 2 of x. Well, when I stick that negative out front, that tells me to reflect over the x-axis. I'm going to reflect over the x-axis. When I reflect over the x-axis, it's still going to go through this point, but where this tails off down, it's going to go up because it reflects. And for example, this point was 4, 2. Now it's going to be 4, -2. So it's going to curve off down here. And now it's a decreasing function. I still have a vertical asymptote, and I didn't shift it left or right. So my vertical asymptote is still at x equals 0. That means that my domain hasn't changed, and my range can never change. It's going to be all real numbers every single time. Because I didn't shift it up, up, down, left, right, my x-intercept is still at 1, 0. And let's look at our next transformed function. The next function that we're asked to transform is log base 2 of negative x. Well, when the negative was out front, we reflected it across the x-axis. If my negative is inside attached to that x, it's going to reflect again, but it's going to reflect across the y-axis. Let's start with our parent function. My parent function f of x went through the x-intercept 1, 0 and curved off to the right. If I reflect this function along what is actually my vertical asymptote is at 0. X equals 0. If I reflect it across that vertical asymptote, instead of having an x-intercept at 1, 0, it reflects over here and becomes -1, 0. So same shape, just the mirror reflection. Do the best you can to draw it the same as your parent function shape. Domain has changed. Instead of from 0 to infinity, now I'm going from -infinity to 0 because of that reflection. Range can't change because it's all real numbers. If I move from left to right, this is a decreasing function now. Number 4, pattern of transformations. Start with your parent function. Parent function has an x-intercept of 1, 0. There is my parent function f of x. For this particular g of x, what transformation am I doing? Well, it's attached to the x inside my function value there, inside my argument. So that's a horizontal shift. X minus 3 moves me to the right 3 units. Now, when I move to the right, I'm going to move first this intercept, this x-intercept. It goes to the right. So it goes 1, 2, 3 units to the right. It ends up at 4, 0. And then I think about shifting my vertical asymptote to the right. It goes from 0, 1, 2, 3 units to the right. So my vertical asymptote ends up at x equals 3. And now I can sketch my function. My function is limited by that asymptote, and then I've got that increase. So domain has changed. Now its limit is not 0, its limit is 3, the equation of that asymptote. Range is going to be all real numbers, and this function is increasing. Okay, one more transformed function. We're going to do our parent function, f of x, where it's just log base 2 of x goes through our x-intercept with a vertical asymptote at x equals 0, right there. And then what transformation do we have here? Well, this is not attached, so we are going to move it up 3 units because that is a vertical shift. Well, if I take my x-intercept and I move it up 1, 2, 3 units, it's no longer the x-intercept, right? If I just moved it up, did I shift this asymptote? Well, no, I did not. That asymptote is still at x equals 0. So my domain and range, 0, infinity, negative infinity to negative infinity. I can sketch my function. There we go. I'd have to figure out what that x-intercept would be. My x-intercept happens when y equals 0. I would have to solve. We're not going to go ahead and we're going to leave that out and not find our x-intercept. It's going to be a fraction. It's going to be a very small fraction. We're not going to worry about that right now. This is an increasing function. Now you'll see that the note at the bottom says to stop and do our 4-2 concept and vocabulary check. I want you to go ahead and pause the video and move to that. Let me take an look at what we've got left here. We've got just a couple of pages left in these notes. Before I break and do that other check on a different video, we are going to finish these guided notes. So go ahead and pause the guided notes, do that concept and vocabulary check, see how you do. I will give you a key to that after we move on from this video. Finding the domain of the log function. Well, remember that for both exponential and logarithmic functions, our base is restricted. Our base is going to be, we usually call our base a, it's going to be greater than 0, and we know that our base is not 1, right? We know that our base is not equal to 1. A is not equal to 1. So our main restriction that we're interested in right here is that a is going to be greater than 0. Because our base is greater than 0, that means that whatever we raise, when we take that base that is greater than 0 and not 1, and we raise it to an exponent, our argument is also going to be greater than 0. Because of that, because of this, the argument will be greater than 0 as well. So we're going to take that and we're going to say, okay, well, if I got f of x equals log base 3 of 2 minus x, well, if 3 is positive, then this has to be positive. So we're going to set that greater than 0 and solve. When we solve, we're going to subtract 2 from both sides and we get negative x greater than negative 2. Now think about this. We're solving like it's an equation, except that with an inequality, if you have to divide by a negative, it reverses that inequality symbol because it changes the way the sides relate to each other. So when I divide by negative 1 to finish solving for x, I end up with x less than 2. Well, what does x less than 2 look like? If I think about a number line really quickly, x less than 2 is this interval, everything to the left of 2 up to 2. So my domain for this function is going to be from negative infinity up to and not including 2. Well, let's look at the next one. For the domain of this function, x minus 5 has to be greater than 0. If I add 5 to both sides, I get that x should be greater than 5. Think about that on a number line, everything to the right. So my domain would be from 5 to positive infinity. Stop and set up that inequality statement just to make sure you don't make a mistake, a quick and simple error that you could have avoided. So I set x plus 2, my argument, set greater than 0, solve for x, and I get that x has to be greater than negative 2. So my domain for this function is going to be negative 2 to positive infinity. But don't forget this first example. It could switch and go the other way. You've got to take that argument out and set it greater than 0 to see what happens. All right, there isn't an any base button, a logarithm button on your calculator. You can't just evaluate any base, just plug it into your calculator, but there are 2 logarithm buttons that you can use. We've got 2 log buttons. We've got common log, log, and we've got natural log, ln. These are both logarithm buttons. If you can't remember which base is which, look at the second function button above it. Above log is base 10 to the x, so log, log is common log base 10. Above ln, natural log, I've got e to the x, so natural log is base e. And in your notes, common log is base 10, and our button reads log. Natural log is base e, and our button looks like ln on the calculator. All right, simplify each common log without using your calculator, When I have log written and no base written down here, I know it's common log, so it's base 10. What is the exponent of 10 that gives me 1,000? Well, 1,000 has 3 zeros, so that's 10 cubed, or 3. Log of 100,000, well, no base written, log means base 10. What is the exponent of 10 that gives me 100,000? I've got 5 zeros, so that exponent would be 5. Log of 1,000th, so 3 decimal places here. 3 decimal places, so it's small, it's going to be a negative 3. Instead of 1,000, I've got 1/1000th. So what is the exponent of 10 that gives me 1,000th? Instead of what is the exponent of 10 that gives me 1,000? See the differences there. How do you know these were all common log? Well, I know they're all common log because it's log with no base written. That's how I know it's common log. Now, the next 3, simplify to natural log using your calculator. And it says to round to 3 decimal places because these we have to round off. Natural log of 1, anything raised to the 0 power is 1. Base e to the 0 is 1. Natural log 10, though, I absolutely have to round off. That's going to be approximate, not equal to. Natural log of negative 6, if you plug that into your calculator, what does it say? If you plug in and you say natural log of negative, don't forget your negative button is down here, negative 6, natural log of negative 6, it tells you domain error. That's because this is outside of my domain. We are not going to have negative values, so it is undefined. How did I know that these were all natural logs? Well, I know that these are all natural logs because it says ln, and ln keys me to the fact that they are natural logs. All right, application problems, more calculator math. Remember, we talked about the fact that exponential functions and logarithmic functions model equations really, really well that show exponential increase or decrease, that show growth or decay. One other thing is heights. Studies show that the percentage of adult height gained by a boy who is X years old can be modeled by this common log function. So here is my log function. 29 plus 48.8 times the logarithm of x plus 1, where x is the age of the boy. So what percent of his adult height is the boy who has the boy obtained if he is 10 years old? So I'm going to plug in 10 for x. So I'm going to find log of 11. Notice that I don't have a base written here. That means I get to use my common log button on my calculator. So for f of 10, he's 10 years old. I have 29 plus 48.8 times common log of 11, because 10 plus 1 is 11. When I plug this into my calculator, I'm going to start there. I'm going to start with log of 11. So common log of 11, enter, times 48.8, enter, plus 29. Well, what percentage of his height has a boy attained by the time he's 10 years old? He's about 79% as tall as he's going to be when he's grown. Let me make sure that because I got a little bit different answer when I did this. Make sure I didn't push a button wrong. I did something a little bit wrong because I got a different decimal. Let me work through that again with the calculator. Everybody makes mistakes, right? So let's fix my mistake. So common log, that's what I'm using, log, common log of 11 is this. And then I'm going to multiply that times 48.8. There's my decimal I wanted. And then I'm going to add to that 29. All right, so I get 79.8%. About 79.8%. He's almost 80% of his adult height when a boy is 10 years old. So then we got kind of a follow-up question. Juan is 72 inches tall. 72 inches is 6 foot tall because there are 12 inches in a foot. 72 divided by 12 gives me 6 feet. How tall was he when he was 10? Well, in inches, we want to know 79.8% of 72 inches. So 79.8% of 72 inches is how tall? So I'm going to do that. I'm going to say, okay, 79.8 is 0.798. Of means times 72 inches means that when he was 10 years old, he was about 57 and a half inches, 57.5 inches tall when he was 10. All right, what percent of adult height has a boy attained if he's 15 years old? Well, this changes because my variable has changed from 10 to 15. So I'm going to do f of 15 is equal to same formula, 29 plus 48.8 common log of 15 plus 1, 16. So when I plug that into my calculator, you should get 87.8%. When he's 15, he's about 87.8% of the height that he'll be when he's grown. If Zane is 68 inches tall, well, 60 inches is 5 foot, so that would be 5'8". How tall was Zane when he was 15 years old? Well, he had obtained 87.8% of his adult height. What is 87.8% of 68 inches? Well, 0.878 times 68. He was 59.7 inches tall at age 15. All right. Studies show that the equation can still be modeled for girls, but it's not the same equation as if it were boys. Girl's height is modeled by this function. Looks a little different. Still, x is how old she is. I'm going to work through this. I want you to work through this on your own and then come back and check your answers. Okay, guys. Here are the final answers for this guided notes section. Make sure you look to see what's next.